Hello everyone, it's November 23rd. Well, I know PCA, Principal Component Analysis. I just had a class, and in the class, the entire process from the start to the end of how PCA works is reviewed. I mean, the first time I encountered PCA was a long time ago, while back in the undergrad, and I didn't understand, not understanding at all. And then later on, I kind of get what it means, like from a very high level. I know what PCA does, and then moving on, I kind of know, okay, it has something to do with eigenvalue and eigenvectors. So that means I can compute PCA by hand. And up until now, I think it's a very, very long journey. And now finally, right, if you ask me, right now it's fresh in my head. So if you ask me to go step by step to show how PCA works, like why, basically the question is why is principal component analysis why does it have a connection with eigen value and eigenvector of the covariance matrix of the given data? Like this question, I can answer. I think the entire process, there's only one weak link that I don't know the proof of. I just take it as value, like the Lagrangian function. I think that's the only part where I don't know the proof, or more likely I just skipped it. I just take it as by face value. So basically, I think what the Lagrangian function says, if the function that you want to minimize, basically it's an optimization problem. You have some function, an objective function you want to minimize with constraints, subject to some constraints, and that constraint is a quality constraint. And if you draw them on a graph, right, it will draw contours, right? So the contours of both the object function and the contours of the constraint, the point where the optimal point is reached is when the two contours touch each other, right? And Lagrangian function says that when they touch each other, then the gradient of the object function and the gradient of the constraint function, they are aligned. They're in one line, right? That is, I think, the only one that I do not have like a complete confidence to say it's true. I mean, maybe I thought, like, no, if I take a shower and then just keep thinking about how the scenarios play out. So because the easiest way to think about the objective function is a cone, right? We think about it as not a cone, like a bowl, and the constraint could be a bowl as well. And then you think about, okay, the two things need to touch each other, right? So when they touch, then we can say that their gradients must be pointing to either the same direction or the opposite direction. That is actually true. And now I'm thinking about it, I have the bowl in my head right now, right? So it's a bowl, and at a certain point you have the gradient, right? So the gradient always pointing towards the value goes bigger. And you have two bowls touch each other. Or you think about the constraint is also a bowl. Then you have two bowls touch each other, and the point that they touch, and that makes sense, right? The point that they touch, then the gradient, they're aligned. Exactly, because they touch, right? They touch, so the gradient must be aligned. If the gradient is not aligned, then they will not touch, right? The touch means, yeah, same thing as like in 2D. You have two curves, right? You have two curves and they touch. And that means the gradient, the slope on that point for the two curves are the same. So okay, so then that weak link is no longer there. So then I have the full proof, a full process to go from reasoning how principal component analysis works. Like we're trying to find a direction of maximum data spread, right, from there, and then explain, well, what does data spread mean? And that means variance, right? Then we need to compute the variance of of the given data along a certain direction, and we want this variance to take the maximum, which becomes a maximization or minimization problem, and we can use the Lagrangian function to do. So this whole process, finally, after so many years, I saw it. Have I internalized it? Probably not. I probably have to go through this many times, maybe a few times in the future, but I have everything written down. So in the future, if it came up, I think I'll be able to just go back, take a look at the note, like, oh yes, I can do this. Like if it's a, if it's an interview, right? A whiteboard interview for some data science position, and then the interviewer said, oh, let's see, do you know principal computer analysis? I'll be like, yes, I know. And then they're like, okay, please do it on the whiteboard. Show me how principal computer analysis derives, right? I think this is a very valid, probably it's not valid. Like in real application, you won't really go through the process of deriving principal component analysis. You would just use PCA. And most likely PCA is incorporated into all the library you use. So for data science, they're high up, right? A very high level. You do need to know like the nitty-gritty, how the sausage is made. If you do research work, I see that. Like if you want to tweak, right? You want to like tweak how PCA works, but on a very high level, I don't really think that's a fair interview question. But it would be fun. Yeah, it would be fun. All right. Anyway, so this is what I mainly did today. It would take a long time to get a whole thing down, but it's something worth knowing. Once in a while, you need to get deep, right? Get deep into the belly of the beasts, right? It's all about math. Right? You boil it down, all about math. I think this is like, what is this? It's application, right? It's application math, not like pure math, not like number theory, right? Those are like pure math, and this is more application oriented because optimization problems. It's used everywhere, right? Control system, engineering, everywhere. Probably software as well, but yeah. All right, let's see. Oh, we have a hard one today. Oof. Have I done it before? Oh, ooh, look at that. My. I went absolutely crazy on this one. Jeez. All right, I gotta do it within 1 hour. I have something going on in an hour, so let's get it started. Jeez, look at this. Oh my goodness. All right, what is this? Largest component size by common factor. You're given an integer array of unique positive integers. Consider the following graph. There are nums.length nodes, number num 0 to thus, okay? There is an undirected edge between nums I and nums j. If nums I and nums j share a common factor larger than 1. Return the size of the largest connected component in a graph. Oh, what the hell is this? So it's 1, 2. Wait, hold on. So 2 and 3, they are connected, right? They are connected because there's an edge if they share a common factor. So what are we returning? The largest connected component. Right, 2 and 3, they are connected because you can go 3 to 6 and from 6 to 2. So they are connected. So basically, everybody is connected. Ooh-wee. Well, the first thing in my head is union find. right? I have the length, numbers value. We can create a array with this size, and then we can union find. Yeah, we can union find, and eventually we just return a counter. We can find the largest, like hold on, what are we given? 2, 3, 6. So we only given the nums, right? So we need to find the edge ourselves. Okay. So what we can do, 2 and 3, no, 2 and 6, they are, so they union together. So 2, 4, 2, 12, so they union, right? They are union. And then we start from 3, 3, 6, right? 3, 6 union, 3, 7 union, no, 3, 6 union, 3, 12 union, and everything union. And 6 with 4. How do we know 6 and 4 are union? They need to share a common factor. How do we find a GCD? Python has GCD, so we can calculate GCD. Yeah, we'll calculate GCD for every single one of them. Hold on, I might have a better idea. How about we just... No, we cannot. Let me think. Because if we calculate GCD every single time, then that's O log n to compute GCD. Okay, so let's say GCD. So these two are no good. These two GCD will be 2. So they will belong. They were union. So we union these two. Union. Union, right? So it will be O(n) squared, right? O(n) squared log n. O(n) squared log n. All right, let's pull out union find. I am not able to write union find by myself. Maybe I can. I don't want to. I don't want to. All right, what are you doing? I'm gonna copy it. Union find. I mean, like if I need to do interview, I might be able to just memorize union find, but it's hard. Actually, where's union find? I think here we can do, let's say st. I think snippet. Yeah, union find. Yep, there we go. That's the union find. And of course, it's the actual name is disjoint set. All right, so we're gonna copy and paste the entire thing. Yeah, but actually, think about it. It's not long. That's it. All right, disjoint set. That's it. That's all it is to it. I'll actually look at it again. So this is the parent, right? And this is the ranking. And a find, we do path compression. So we say we're gonna find if my parent, if I'm not my parent, then we need to find my parent, right? So we're gonna find using my parent, right? And then eventually this one will compress everybody to one value. Then we return this. Okay. Union. We know X and Y needs to be union, so we need to find their ranking for. Wait, hold on. This is not ranking. This is the parent. So we find their parent. If the parent is the same, means they already belong to the same union. If not, we compare their rank, and we assign the higher rank, right? So I say this rank is smaller than this, right? And then we assign the parent of, actually the parent of this parent, the parent of the grandparent. We assign the grandparent of X to the parent of Y, right? So because Y has higher ranking. Otherwise, we do the other way. If they have the same ranking, then we just arbitrarily, we say we're going to assign grandparent of Y to X. And once I assign that, we're going to upgrade the ranking for x because we use x's parent. So x's parent's ranking, we use that ranking, we use that as a parent. Yeah, makes sense. Again, if we have to write it myself, it's gonna be tough. Okay, so for this one, what do? We need to create a DSU. So create DSU will equal to DSU. We need a n. What is n? N shall be the largest value in nums, right? Because every value needs to be it shouldn't be n plus 1. Range n. Every single value needs to be inside, right? Oh, I can manipulate it. Numbers is, so I can just say max nums, right? Max nums plus 1, right? Because these values are 1 based. Okay, so we have this joined, and Python GCD. Because I was also, like, I'm also thinking about, if I sort, right? If I sort, and every time I do GCD, I will divide by the common factor. So everybody will be dividing the common factor. I don't know. I'm not sure. I think I'll just go GCD. We have math.gcd. That shall be sufficient. Return the greatest common divisor of the two integers. Just make sure they're not 1, right? Just make sure they're not 1. So import math. Okay. So basically what I'm gonna do for I in range and nums, right? For j in range I plus 1 to len nums, and we say if nums I, if GCD math.gcd nums I nums j, if this one is larger than 1, right, then we say DSU dot union nums I nums j, right? So run all that, then we're gonna return return what? So we need to do a counter, right? So let's do a counter. So from collections, I'm gonna import counter. So we're gonna count so when you do a counter, DSU dot parent, right? So I'm gonna counter the parent, and we're gonna pick the maximum of this, and key will equal to, actually no, just dot values. Okay. All right, let's try this. So we have a couple of test cases. The first one shall return 4. Oh shoot. All right, this one return 4. Second one shall return 2. All right, this one shall return 2. The last one, oh my god, I do not remember this at all. It's actually quite impressive. It's all the connections. Alright, so here is nums, and that's it, nums. Largest common size nums. Alright, let's try it. Yep, I think this will work, but the runtime is, OMN. Can we do better? Let's try it first. Maybe this one will pass. Who knows? All right? Maybe this one will pass. Let's try it. Let's hope it will not time out. Based on the time, looks like it's going to take a long time, so maybe it won't time out. If it does, then it just does. It looks like it's going to time out. Oh, we have a wrong answer. Ah. How? Expected 9. What the heck? Expected 9. Result is 6. Huh. Interesting. Can we print? Oh shoot, that's gonna be a long. Let's be smarter. So for n in nums, right? We're gonna print dsu dot parent n, and we're gonna do n and this. All right, let's see. So n 65. The parent is 76. Huh? That doesn't make any sense. 43 is by itself. So I have 76. Hold on. I need a piece of paper. 65, right? So we have 65, 35, 43, 76, 15, 11, 81, 22, 55, 92, and 31. Okay, so 65 essays to 76. That's fine. So 35. That's right. Let's give us a union. So 35, 65, 35. Right. So 65, 35, 55. Right. And 55 have 11, so we will have 22 in it. Because we have 22, so we'll have 2, so 92 will be in it. And 76 will be in it. Oh shoot, 15, 11, 81. It is 9. Alright, which one is not? So 65. I'll probably need to do one more compression. That's probably it. So let's see, 65 point to 76, right? And 35 point to 65. Yeah, we need to do one more round. One more round of what? Just find, right? One more round of find. So I think we just need to say dsu.find n. Right, just do one more round of compression. And after compress, this one will pass. Yes, we just need to do one more round of compression. So at the end, before we return, right? Before we return, we need to do one more round of compression. Now we go. That's probably timeout. Yeah, it's on squared. Yep. Okay, all the time limit exceeded. That must be my previous attempt using the same solution. All right, so we're back to square one. This definitely takes too long. Well, GCD might take too long as well. Can we do better? I mean, we can. Can we? I mean, how can we do better? What does it mean by doing better? Well, doing better means let's say in this case, right? I say I'll find, if I sort everything and I pick the smallest value and we're trying to find if anyone is a factor of the smallest value. I mean, hold on. So the point is to huh, 2 times 10 to the 4th. 2 times 10 to the 4th. Shoot. What do I do? What do I do? Factors. How about factors? We have 2. So let's say we're going to divide everybody by 2. All right? So we divide everybody by 2. Okay, so 2 is gone. And anyone who can be divided by 2 we'll group them together. All right, so after first round, we will group 2, 6. Yeah, we'll group 2, 6, 4. I'm looking at here. 2, 6, 4, 12 together. All right, that's first round. Divide by 2, and we'll indeed divide by 2. So what we return is 1, 3, 3, 7, 2, 6, 21, and 39. So we can, if you can be divided by 2, we will take 2 away. So that means we have grouped everything that has a factor of 2. So next one, let's do 3. Right? Let's divide by 3. So if the value is smaller than me, so 1 we just don't consider. So now we go 3. So we handle 3 and 6. Right? How do I know it's 6? Well, I need to copy it. I need a copy. Okay, so I know 3, 6, and the 3 will be 1, this will be 1, and it's actually when it's smaller, I just don't consider it. So 2 cannot be, that doesn't matter. So I have another 6, 12. So 12, right? 12. So 3, right? 12. That will be 2. And 21, 7, 12, 21, and 39. All right? That will be 13. So who else is not in? 7 is not in, right? So that's that. So we do 3. So next round we do 5. So we go around, try to divide by 5. Nobody is divisible by 5. Yeah, if it's smaller, we just let it go. If it's larger, then we're trying to see if it's divisible by 5. And it's not divisible by 5, so that's it. Now next one is 7. So we have 7, right? So we're going to do 7. And we have another 7 remnant. So now 21. Now 7 is inside. Once 7 is done, so this will be 1. This will be 1. All right? And when do we stop? We stop, like after doing 7, we already grabbed everything, right? When do we stop? Well, we stop when everybody has been factored, right? So when everybody has been factored, what does that mean? That means when you go through there, like when you hit a certain prime number, then but all the remaining is smaller than the prime number. That means we have factored everyone. And when that happens, then boom, we're done. So at the end, we're gonna go to 13. We're gonna go to 11, right? Well, nothing. And we go to 13, and we have one of them, right? So we have a one of them, so that one will be by itself. So how do we handle by itself? Well, if it's by itself, then we don't do anything, right? If it's by itself, yeah, we just don't do anything. Okay? And then next round is, what's 13, 14, 15, 17. 17 comes in, nothing. So that's it, we're done. And given the value is 10 to the 5th, right? If the value is 10 to the 5th, we just need prime numbers up into 10 to the 5th. Think, can we go like a little bit smaller than that? Yeah, we can go just square root. Square root 10 to the 5th. Square root 10 to the 5th because then when you divide by that will, then yeah, we hit there, the remaining will definitely be smaller. No, actually not. There will be prime numbers. All right, there will be prime numbers. And we're not making it any like smaller. So this one is 10 to the 5th, 10 times 10 to the 5th. And now we go prime numbers. That's going to be a lot of prime numbers to go through. Hold on. I feel like it gotta be an easier way, right? Gotta be an easier way. We can also like do GCD as well. Well, GCD doesn't work. I mean, we can GCD them, all right? And once I GCD, I will divide. How about that? But how do we GCD them? We go smallest one, GCD everybody. Okay, I'm listening. Smallest one, GCD everybody. And this one, GCD everybody. And at a certain point, no, that's still, yeah, what if I have a gigantic prime number? I do have to go all the way to there, right? Well, what if we think about it? We can always remove, right? We can always remove the value. We can turn this into a set because every value is the same. Well, if it's a set, we cannot change. Which is fine. It's just like a, how should I call it? A queue, right? Think about this as a queue. And everything come out, and if the current prime number is larger than whatever is remaining, and that one is discarded, right? And then we just keep going, right? We just keep going, and because every time I use a prime number to check, and if a certain prime number, hold on, if the remaining We can look for the prime number directly. So we don't have to go through prime number one by one. So we have a list of prime number all the way to 10 to the 5th, right? So we have the list of prime numbers, and we're gonna sort this one as well. So we're gonna sort this, and we go from the smallest, right? And we're gonna find the prime number that's smaller or equal to the starting. Smaller or equal to. If the prime number is larger than, like current prime number is larger than, then I just got it. So for every one, I want to find a prime number that's smaller than me, right? Now we have to go prime number one by one. Prime number one by one. How many prime numbers are there to 10 to the 5th? I think I asked this question a few days ago. Prime number up to 10,000. No, it's 10 to the 5th. Holy, that's 5 zeros. That's 4 zeros. Now that's a lot. That is a lot. Wait, can we do square root? I think we can do square root, right? Hold on, what's the rule of square root? What do we want to say? We want to say we have a bunch of prime numbers, right? And we're trying to use these prime numbers to factor the values in the nums, right? And then what we're saying is if we go to a certain value that I cannot factor, then anything bigger. Yes, we don't have to go to 10,000. We just need square root of 10,000. Well, it's not 10,000, it's 100,000. Square root of 100,000. That's 316. That's 316. Come on. That will be good. Right? That's only 316. Not factor. Can we go prime number up to, let's say, 1,000? Gotta be something like that. Prime up 1 to 1,000. Okay. Please be in a nice. Not too bad. So 315. So we go 316. We go 317. Right. So these are the prime numbers. So we have 300. Right. At most 300. And at each time we go through this whole thing. So that's not 10 to the 5th times 10 to the 5th. That's 300 something times 10 to the 5th. Okay, so this one we timed out, but it's fine. We have solution number 2. All right, so this one, TLE. Let's go solution number 2. All right, so basically it's the same idea. We're gonna go this, so use prime numbers to factor. So primes. All right, now we're going to copy and paste all the prime numbers. So we have, what do we have? We have these. Probably will be a nice idea. Let's do this. 100, 200. All right. What's next? To 300. What's next? To 317. All right. That shall cover. There we go. So we can copy this. Boom. All right. So that's our prime numbers. And we do this. DSU, we do this, right? And we're just going to say for P in primes. Right? Now we're just gonna go one by one, right? One by one. And we're gonna just discard as well. So what do we do? Temp. Let's do it as a Q, right? So for n in nums, if P where n mod p is equal to 0, let's say, so we need a temp, and we need something to group things with, right? Something to group things with. How do we group things with? We group it by the group. All right, group is -1. So how can I say group is 0? So if this, right, and we say if not group, then group equals n. So that's the start of the group. Else, if we have a group, then dsu.union union what group and n. And after that, temp dot append n p. All right. So that's this. If n is larger than p, right? If n is smaller than p, then we don't append. So temp dot append n. If it's larger than p, we just add it. And when we go through everything, we say nums equals temp. I'm changing nums, but that's fine. Nums equal to temp. So we go back up, group is this, we'll do it again, and every single time the list will shrink, right? The list will shrink, and eventually we're gonna do these two. Ooh, you don't have nums anymore. We do not have nums anymore. That is an issue. All right. Do we need to copy the nums? Can we just okay, every single one? I don't like this idea. I think I like this idea more. Let's just copy it. Yeah, let's just copy it. This is the q, and q equals this, and we can do this. The nums doesn't change. Now we can compress and try it. Oh, wow, it's ugly. This is no good. All right, let's go the easy one. Hold on, I'll be back. Well, I know why it's not working. Because I start with 2, right? This one gets discarded, this one becomes 3, and these two remaining. Next we do 3, so this got discarded, and this shall be, and this shall union. Oh, hold on. It has to be 15. It has to be 15. Because I only divide by 2. Let me think about it. I only divide by 2. Alright. So first is group is 4, right? And then next one is 6 comes out. 6 can be divided. And then we're gonna union 4 and 6. And temp gonna append 3. And next one is 15. 15 is not. So I just append. So it'll be 2, 3, 15, 35. So coming back again, p is equal to 3. So first one, 2 is actually discarded. The next one, 3. So this one is actually equal to 3. It's now 6. That is the problem. So we need to push in the value and the index. That is, yes, we need to push both. So Q is not this. Q is going to be index n for in enumerate nums. Right? And then there's going to be for in Q. Blah, 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 group. And that's not equal to n. That's going to equal to nums I. Otherwise, and group nums I. And we're going to append, same thing. We're going to append I and n divided. Otherwise, we're going to append in. Right? And do this, blah, blah, blah. Once we're done, we'll check out. There we go. This one will pass. So we have index. They all pass. All right, let's try this one. Let's try this one. And of course, we are going to try this. Oops. Oopsie daisy. Hold on. I think I delete the DSU. Can't have the DSU. Alright, that's the one. Yeah, let's try it. Let's go. Come on. Come on. Come on. Oh, wrong answer. That is different. Shoot. That'll be hard to debug. That will be hard to debug. And actually, I think we're even gonna hit. Like if I provide a large prime number, isn't this going to be 84? I just realized, like, if I provide a large prime number, this loop will never end because it will never be 1, and it will always be larger. Right? Oh, but my P is going to exhaust. So I run out of P, right? We run out of P, and so I have something left in Q. Is that why? I don't know. Do we have something in Q after it's all done? Yep, we do have something left in Q, and they are all big values. And we have run out of prime numbers. Are they all prime numbers? Apparently one of these is, oh no, these values are already changed. And no. They might already be added already. They probably got added already. Oh, this is not useful. Oh man, this will be hard to debug. Oh, we're only past 72 cases. Wow, This is a hot. I think this. I probably already put this in Nightmare. What the heck? Oh, I have a correct solution. I have a correct solution. Nice. So this is what we can do. Solution 1 will be correct. So what I want is solution 1. We're going to print. Holy guacamole. For n. Oh, we can do for n in nums print, right? And dsu dot parent. I'll do the same thing for solution 2. It's kind of, to see. So we have sol1, okay, sol2, and we're going to do sol1, and you know what? I'm just going to run this again. It's fine. That's sol2. Okay. So first one pass. Let me just do copy the whole thing up until here, right? And let's put this in a diff. So online diff. All right, diff checker. Original text. This is our original text. Oh, come on. Oh, I'm gonna copy the entire thing. Can I copy the entire thing here? Yeah. So we don't need this, right? And this one will go all the way up until here. All right. And oh, I just realized that everybody's different. Okay. 2 is grouped with 7, and they are grouped with 535. And which one does not get grouped? This one, 463. 463. 463 divided by, well, it cannot be divided by 7. 463. Why can you guys be grouped with 7? We had 535. Wait, 453. 11. No. 7, no go. 13. 17. 19. Wait. It can be divided by anyone. Wait, somebody can be 463. These are prime numbers, that's fine, right? These are fine. Yeah, the problem is 463, which means somebody must be 463 times something. It's only explaining times 2. 463 times 2. 926. Do we have a 926? Do we have a 926? 926? No, we do not have a 926. Wait, is 463 a prime number? Yeah, 463 is a prime number, okay? So 463 is a prime number, but I say here 463 can be grouped with 7, which means some value is 463 multiplied by something. 463. Hey, do I even have 463 here? No, that is not the same value. Come on, man. It changed. Yeah, stupid. It changed. These are the prime numbers. Okay, so we say 926. 926. There we go. That's 926. So the reason we didn't find is because we didn't go high enough? Are we saying we have a 463 left? It must be, right? It must be, because I didn't hit 463. Yeah, so I hit whatever I hit, right? I hit the prime numbers, whatever prime numbers I hit eventually, I think 300 something, right? So then 463 is not hit, but we hit 2, right? We hit 2, and that means by the time we finish all the primes, we need to go through the list again. And why do we need to go through the list again? Well, that just means we have removed the majority of the values, right? So we're going to go through the list again, and then the remaining values in the list must all be prime, because I already hit all the prime numbers all the way. So the remaining all be primes, but there is still possibility that within these prime numbers, they will be something might be the same. So what do we do? Well, what we do is we are just going to sort the queue, okay? So we're going to sort the queue based on this value, and we're going to go one by one, each one come out, and try it, right? So we try if it's to do this, divide by this, and this divided by this divided by this. So every single one is a prime number, and we just need to find if anything in that case, basically we're saying in the remaining, right? In the remaining, and they are either prime numbers. Yeah, they must be. The remaining value are all prime numbers. Are all prime numbers. So I just need to group them, right? I just need to group them. Go through every single one. Yeah, so yeah, I just need to group them because the remaining are all prime numbers. So they cannot be factored anymore. So I just pick the same prime numbers and then union them together, which means I would just go through every single one and yeah, hold on. So one more step. We're gonna do the last one. We're gonna call it groups, right? It's gonna be like this, right? And we're gonna say for in in Q, right? If n not in groups, then groups n equals nums I, right? else, if it's already in it, then we're just going to say dsu.union groups and and nums I. We'll do this, and then we're going to define again, and then we run it, and then we pass. All right. So that is the spirit. That is the spirit. So let me just comment out this, run everything. We forgot to put this. All right, run everything pass. Okay. So that's my last attempt. So this is to handle the case where there are ununioned values after there are ununion values, and after turning every number to a prime, e.g. If we have 463 and 926 and 926, they will not be unioned during the search, during the prime checks, because the prime check stops at 317. But the prime check does reduce 926 to the prime value 463. Right? Thus, we can just union all the prime values that are the same, right, in the remaining queue. All right, let's try this. It's my last shot. If it doesn't work, I do not know what to do. Come on. The last shot. Okay, let's run code first. Let's make sure everything works. Everything's still working. Okay. All right, let's try this. Come on. Come on. Let's go, let's go, let's go, let's go, let's go. Oh. It's not enough. Holy guacamole. How? How is it not enough? Oh, man. Every value shall be reduced to its prime version. How is it still not enough? This is bonkers. Shoot. What's the answer for this? 439. Which one? Which one is the culprit? Let's find out the culprit. And actually, I'm going to say in sorted, so it'll be easier for me to handle. All right. This is unbelievable. I'm going to run it. It'll take a long time, but we will have this. Well, let's handle it here. All right. So everything all the way up to where? Should be 13. Shoot. All the way here. All right. Alright, so I'll do it again. Right here, I'll do it here. Alright, this is this text. I have this. Find difference. 2062. Okay. No, actually, this is not helpful. Yeah, I will not be able to know which one is triggering the problem. Right? We don't know. I can see. I don't see. Where is the thing that differs? I think I need to change all 2062. I need to change that to 13 in order to see. Hold on. Maybe I need to do that. So how about we change this to 13 and then see what happens. There we go. 1423. I have another one, it's 13. Well, that's actually 2062. 2062. Why is this one 1423? Oh my god. 1423 times 2? Do we have a 2846? We don't have a 2846. How about times 3? Do we have a 42? This will be easier. Do we have a 4269? No, we do not. Times 4. 5, 6. We have 5692. We have 5692. Yeah. 5692. Okay, so I just want to also print out. So we're gonna not do this one. Let's do the second one. What do I want to print out? I just want to print out a Q, right? So actually, I don't need to print this. I just want to print out a Q. Print Q. Right? Oh, jeez. What the heck? There's a lot of values. 1423, right? So 1423. No, what we want to find out is 142. Okay, so this is we don't print out the Q directly. Let's do this. All right, I'm gonna say for I n in Q, if nums I equal to 1423, print n, print nums I, right, and n. And if nums I is equal to 5692, I'm going to print again. So print nums I and n. So, oh shoot, they are not. Wait, really? After I divide all of those, it divided by 2. Oh, mamma mia, that is correct. I had to divide it by 2 multiple times. Oh, we have to take away all the factors, not just one, all the factors. Ah, I see. So, we're gonna here for this, if this equals, so, interesting. Very interesting. How about while n p is equal to 0, all right? And then how about this? If this, now group, blah, 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 but we don't do this. We say while not n, n p is equal to 0, right? We do n divided equal p. Remove all the p. Once you remove all the p, then we're gonna do n, right? So if it's this, it's gonna be this, and we can say if this equals to this, else if n is smaller than p, then we just continue, and we can do this. How about this? Going, there we go. Now we're reducing, right? Now we're reducing everything. Okay, so again, comment out this. I'll go through every single one. Everybody pass. All right, last shot. Come on, I'm running out of time. Last shot. Last shot. All right, let's go. Last shot. Come on, show me something. Show it to me. All right, we're gonna run this first, just in case. Go, come on. Yes. Well, it looks bad, but we did pass. Oh my goodness. This is still hard. Ha! This is still hard. Wow. What a problem. Actually, I think I spent them all at the same time, right? From the first to the last. It's about an hour. Jeez. That's tough. Alright, so I really have to go, but wow, this is a tough one.